So welcome to today's webinar about the SustainablE Steel Additive Manufacturing project, SESAM. I'm Jule Wegen from EIT Manufacturing, and I will be guiding you through the session today. The SESAM project is about how laser-beam directed energy deposition with wire can be integrated into duplex stainless steel production, and it's funded by Vinnova, the Swedish Innovation Agency. And today's webinar is very exciting for us because it concludes the 3.5 years of the project, and it is about the main learnings from different angles that will be shared. So on the agenda, we have first an overview of the project by University West and an introduction. Afterwards, we have challenges and process overviews and also solutions by PROCADA, followed by comments on the metallurgy of additively manufactured duplex stainless steels. And we close off with notes on sustainability, also by University West, on traditional machining versus additive methods from an environmental sustainability perspective. And at the very end of the webinar, we will have also space for questions and answers. And please note that this webinar will be recorded up until the session of questions and answers. All right. So now I would like to hand over to Jörg Borg, who is an associate professor at University West and also the project leader of SESAM.
I just want to give you a very brief overview and introduction into the project. You see all the partners that were contributing, and it was funded by Vinnova. So when we started, we had basically one goal, large industrial interest into the wire DED with the laser, and with a very specific stainless steel that we are looking into. And of course, when you look into this, there are always challenges and obstacles that you face. And these ones we defined, of course, and try to figure out how to overcome them regarding, for example, printability, then also the microstructural changes that appear in this new process. And of course, very important are the mechanical properties and also the corrosion resistance in the end. So the big goal of this project was to find the right parameters for printing such structures and having minimum defects and the correct microstructure as well to achieve the properties that we actually need. So once we identified that, you see on this graph on the left side, we started with the challenge. We identified them. Then we did a lot of experimental work. So you will hear about that from Peter later, what we did with the process optimization. And then there was, of course, also an extensive work into microstructural analysis. How does the material actually behave afterwards? And since we wanted to go quite close to production, we also had some efforts into machine development and did also the validation after that. Then at the end, there is part production also. We produced a lot of different parts and analyzed them. And as you will see, we'll also talk then about the sustainability aspect. So how does that affect the company manufacturing? The process that we are talking about is the wire DED process. Here, a very simple sketch. We are heating with the laser the material. Already in the picture, there are some challenges. You see the gas shielding, the temperature fields that are evolving. So there are these challenges that will be addressed today. Yeah, as I said, we are going quite high TRL. We started around 5 in the beginning. So it was clear that the material can be processed. In lab scale, it was demonstrated. And we went higher to TRL 6 and manufactured a lot of demo parts. And then in the end, we analyzed a lot of material results and process results to reach TRL7 actually. With that, that is the basic principle, the procedure that we had in SESAM. And then I will give the word to our experts. We will hear first about processes, process stability in general, then about the material, and in the end about sustainability. Thanks for joining the webinar, and yeah, I hope you have a lot of questions and input later.
Okay, good. Yeah, so I will be talking about the challenges that we faced and the solutions that we developed within the SESAM project. And me too, I will start with discussing a bit about the process. So as previously mentioned by Jörg, this is a laser wire AM process. Formally, it's called DED-LB /W, which is, that's just a beautiful name. But that's what we have. It's also called LMDW sometimes, or DDW, or just laser wire AM. Well, what it comes down to is that we have a metal wire as a feedstock, which is fed into a melt pool created by a laser and assisted by electrical preheating. So we're feeding electrical current through the wire. And we have a manipulator to move this thing around onto a substrate, and it's usually an industrial robot. It could also be a gantry system. Within this project, we've used industrial robot. So I will be showing quite a few videos and pictures today. So just to set the scene, this is a picture from the top, and you see the wire entering from the right side, and you see the dark red part here is the laser spot. You see molten material to the left, and we're moving to the right in the picture. And this is what it looks like. This is a high-speed footage of the process. So you could see the wire is moving, it's being fed into the melt pool. You could see that it melts on the top. There's a darker shade on top of the wire, but also on the sides, you could see it melting. You see that the melt pool is a bit dynamic. There are waves going back and forth. You could also notice that underneath the wire, what you see is a roundish shape, which corresponds to, let's see if I can get my pointer here. This area is illuminated by the laser, the light area. The dark area underneath the wire is not illuminated by the laser. So in this picture, it corresponds to this area where the laser is shading the melt pool. And you can see these shapes here, which looks, we call it a horseshoe. It doesn't really look like a horseshoe, but there's an indentation in the melt pool here where we don't have as much molten material. This is important for later. So this is, you see the time scale here. This video is 4,000 frames per second, but you could also see that the wire is moving quite quickly compared to how fast we move to the right. So if you look just here, you could notice how, you could get a feeling of how quickly we are moving to the right. And then you see the wire is moving much faster than that. So the goals that we sent up in this project was that we were to reach a deposition rate of 5 kilos per hour of duplex stainless steel. 2205 was the target material. We were also getting into other alloys, which might be discussed by some other speakers later today. And the goal was also to get forged properties. And that is primarily determined by the fatigue life of the part. So the dimensioning, requirements for the material is not static properties, but fatigue properties. which makes it much harder in terms of building this material. And why is that? Well, that's because there are defects, or we try to avoid defects. And whenever we have fatigue stresses or fatigue cycles, any kind of defect is much more detrimental than in static with static property. And why do they occur? Well, they occur due to excessive variations in process state. That's a fancy way of saying that when something happens when it shouldn't, and it's worse than we can tolerate, then we get a defect. And the most detrimental types are lack of fusion defects, where there's not enough energy instantaneously to transfer to the wire. That might be a global phenomenon, such as if we suddenly get a drastic reduction in the electrical preheating or the laser power, or it might be a local phenomenon where, for example, the underside of the wire is shaded and we don't get enough energy into a certain volume element. And if that volume element hits the unmolten substrate and it's not melted, not properly fused, then we get what's called a lack of fusion defects. These are usually only two-dimensional. They have very negligible thickness, but they are very detrimental to fatigue life. There are also pores, which comes from an agitated melt pool. So basically, if the melt pool is not flowing nicely, evenly, if it's got waves going back and forth, and if we've got crashing waves, we might capture a part of the surrounding atmosphere and it might get enclosed and solidified in the melt pool. And then that gives rise to a pore. We might also have inclusions, which is typically come from some kind of contamination. It could be something in the atmosphere, but it could also be introduced through the feedstock material. So in this project, we are targeting high productivity parameters. That means that we have smaller margins overall for all of these. So whenever we, let's say, press the accelerator pedal and we go faster, the margins get smaller. So you need a bigger highway or a better driver. And in this way, this case, we can't do very much about the highway. So we need to have a very good driver. And in our case, that is the high performance control system required to maintain this process state and to avoid the defects. So as I mentioned, the challenges here in the process is that we're making a 5-fold increase in deposition rate compared to the baseline we had prior to this project. In order to do this, we needed to increase the power, of course. There is more material to melt, so we need more power. We can't just increase the laser power without increasing the laser spot size, because then the power density will get too high and will just evaporate the material or a large portion of it. So we need to increase the spot size. And in this case, we had to stick with the optics we had. So we went with a specially purchased fiber which had a core diameter of 1500 microns, which is a very thick and very fragile fiber. We also had to increase the power in terms of hot wire preheating. So instead of first converting electrical power into light and then light having the light heat up the material, we're just having the electrical power going straight into the metal, heating it up, which is very efficient, but it's also a bit risky, because if we introduce too much electrical current, we will get an arcing event. And these arcs will create small explosions, which could agitate the melt pool, and thus, as we learned previously, lead to pores. When we increase the overall laser power, there will also be reflections, because roughly maybe 40% of the power, laser power, actually goes into the material. The rest will be reflected. And that that needs to be taken care of, because we have sensitive materials, sensitive equipment in the chamber. And if you were to point a 5 kilowatt laser beam at that equipment, unless it's properly cooled and reflective itself, it will burn. So there was a lot of engineering effort spent into cooling stuff and shielding stuff. Basically, we are introducing maybe, well, in the worst cases, or the maybe 15 kilowatts of power into the processing chamber, which means that unless we want everything to get hotter and hotter, we need to also get rid of 15 kilowatts from the processing chamber. So that means that everything that went in there, which isn't supposed to get hot, must be cooled and must be water cooled. We spent very much effort onto this. We also needed to deliver more wire. So that requires that we have good feeding, that we could feed with a sufficient speed, but we also have need to feed with low enough variations. So we need to keep a very steady pace of the wire that we feed. And that has requirements on the whole feed delivery system. Where do we have our motors? How long are our liners in which we feed the wire? And how do we control it? And then there's also the issue of the surface quality, because the surface quality of the wire is both how, if there's any residue on the wire, and when we feed a lot of wire quickly, any residue will accumulate, and it might get the wire to stick in a nozzle and might not be properly fed into the process. But it's also a matter of, if we have a wire which is very rough, has a high, a poor surface roughness, then that will wear out a lot of equipment due to abrasive wear. So we need to increase the power, deliver more wire, but we also need to maintain the stability. Because if we don't, we could agitate the melt pool, or we could not properly melt the wire and thus introduce defects. And as a measure of this, we need to, we have 43 milliseconds to thoroughly melt the wire from that it enters the melt pool until it's otherwise would hit the bottom of the melt pool and interact with the substrate, giving us an LOF. So that's more or less the time scale that we're working at. And the faster we feed the wire, I mean, if we were to double the feed rate or the production rate, this would go in half unless we change the diameter of the wire. So I have two 10-minute slots which are baked into one. So now you'll have to continue listening to me for another 9 minutes or something. Hope you're okay with that. So the process control that I've been mentioning that we've used in this process, I went in a bit deeper last time in our last seminar in the SESAM project, but now I will go through it very briefly. We use the wire tip as a sensor, and if you look onto the figure to the right here, you'll see the top one where we have a wire which is entering a melt pool where we have a bit of a neck. So the molten metal wets onto the wire tip, and this is what we want. This is the nominal process state, because we can be quite sure that if it looks like this, the wire is not interacting with the unmolten substrate, which you see here. So the middle portion here shows you that the wire is actually too far down. So there is a significant risk here of the unmolten wire protruding through the melt pool, interacting and exerting a force onto the substrate, which would typically lead to an increased risk of a lack of fusion. There's also at the bottom here another unwanted state, which is where the wire is positioned too high. And this will typically lead to this very weak neck here to be broken, and then we get droplet transfer, which is not as detrimental as the middle here, but you would get an uneven surface and it might be harder to continue depositing. And also you will, when you don't have electrical contact between the wire and the melt pool, you're no longer transferring any electrical energy, so that you lose a lot of power. So how do we maintain this top situation? Well, as I mentioned, we use the wire tip as a sensor, and the electrical current that goes through the wire, we measure it very, very accurately and quickly. And by basically measuring how the resistance of the melt pool changes, we could determine, or we could tell the difference between these three cases. And what we do is that we say that, okay, we want it to look like this. So we lock in this resistance and we ask our controllers to maintain it by moving the wire up and down, by changing the wire feed rate, and by adjusting the electrical power. And in addition to this, which is our primary control system, we've also within the SESAM project developed a new non-contact wire feed sensor based on optical methods. I won't tell you much more, but it allows us to very accurately and with a very high sampling rate determine the actual wire feed rate. And this is has been a key in order to understand some of the issues that we've faced in this project with white spots that Asun and Björn will talk about later. So our controller compensates for variations in terms of geometry, which could be due to a deforming substrate or a non-nominal substrate if it's not it's out of specifications in some way. It also compensates for variance in wire feed rate, because the wire feeder, we want it to always give us the feed rate that we ask of it, but it won't. There will always be some kind of variations. And in this project, we found out that we have a window of maybe plus minus 2% in the wire feed rate. If the wire feed rate goes outside of that window, we get a defect. And when we benchmarked the different wire feed systems, we see that even the best ones typically have a natural variation of up to 5%. So without the control system, we wouldn't be able to deposit with this high rate at all. We also compensate for variance in input power and workpiece temperature. There is a mechanism that to some extent adjusts the process so that we could take care of less or cooler substrate or hotter substrate by moving the wire up and down to absorb more or less of the wire, more or less of the laser lights onto the wire. And now I'm going to show you a video. In the top video, we do not have the control system active, whereas in the bottom we do. And if we go back to the beginning and we run it again, you'll see that there's a big slope here. We're going downhill. So this is to show that when we really provoke the system, when we have the feedback control system at the bottom, the wire is moved so that we always maintain a sound process. The wire is actually, if you look carefully now that we're going back up again, you can see that the wire is moving upwards. So the actuator is constantly adjusting the position of the wire to follow the substrate surface. And this is what it looks like when we're done. So to the left here, you see the profile that we try to follow. And to the right, you see what it looks like when we're done. So we're not only able to follow and maintain a good process, we're also able to smooth it out or repair it. And we do this by when we detect that the wire needs to move downwards like this, that means that we need more material. So within the process window that we've established, which is how much more wire can we add without it getting too cold, we make sure to add that wire. And in the opposite, when the wire is going upwards, that means that we have sufficient material so we could remove or reduce the amount of wire that we introduce to the melt pool. So we can take an uneven substrate or some other variation that the process might throw at us. Thermal variations, variations in feedstock delivery, power input, any kind of variation will be compensated for by the system. And that's what I'd like to press home here, that building this quickly with this process wouldn't be possible without the control system. Because we have it's such a narrow process window, so maintaining it would be impossible without this automatic control. And if you remember that, I mean, this is also a high-speed video, I forgot to mention this. This is, I don't know, maybe a second worth of video. So everything happens very quickly, and it's impossible for an operator to accurately interact with this, because the operator will never see the high-speed video like this. The operator would just see something blurry and need to act immediately, which is impossible. And it's also not repeatable, and it's not something that you could rely on for production. Yeah, that's everything for me.
Great, thank you so much. Now, the next part, I would like to hand over to Asun Valiente, who is an associate professor at University of West. So please, Asun.
Thank you. Yes, most welcome, everyone. Now, in this part of the presentation, we will talk a bit more into microstructure and properties. And everything that you will see in this presentation has been, produced or investigated by Alfa Laval, Boiler Welding, and here at University West. So we have compiled everything in this presentation. Yes, let's have a look at these microstructural challenges and properties. Very, very quickly, very short crash course on duplex stainless steels. Duplex stainless steels are stainless steels having a dual phase, austenite and ferrite. With the austenite, the material gets ductility, toughness, and general corrosion properties. And with the ferrite, we give strength and resistance to stress corrosion cracking. And then, of course, there are different variants of duplex stainless steel. So we have from lean duplex to hyper duplex. And the difference is the alloying content. So when we increase, especially chromium, we get higher corrosion resistance and higher strength. And in this project, we focus only on the standard 22% chromium duplex stainless steel. And of course, it has a lot of different applications in the oil and gas industry, petrochemical, pulp and paper, and salination. So these are very, very, crucial areas for these materials. If we look into the phase diagram, the diagram under equilibrium, we will see that duplex, let me find the pointer now. Yes. So when the materials solidify, it's fully ferritic, basically fully ferritic. And then if we give time and opportunity, part of the ferrite will transform into austenite. And the ideal point is that we get this 50-50%, so 50% austenite, 50% ferrite. But what happens if we dry very fast? I mean, if we have a very fast cooling and we don't let the material to solidify under equilibrium conditions. So what we get in these conditions is we cool very fast. is that we basically get a fully ferritic microstructure. Here you can see, I forgot to say, everything that you will see white in these microstructures that I'm showing is the austenite, and everything darker is ferrite, and everything super darker is the nitrites. So these nitrites are chromium nitrites, and then I'm gathering a lot of chromium around, so that depletes the corrosion resistance. So what happens when we have a very fast solidification? We have a huge amount of ferrite, the formation of these nitrites, and then the material is not so good for corrosion resistance as we wish. But what happens when we have the opposite case, when we have very slow cooling, or as we have in case of additive manufacturing, we have repeated heating? Then the thing is that we end up forming this undesirable phase, the sigma phase. So ferrite decomposes into chromium, and body segregates and form these intermetallics. So that can end up with embrittlement, less corrosion resistance, and less impact toughness. So this is very detrimental, especially for mechanical properties. So, okay, if we drive very fast, it's not good. If we drive very slow, it's not very good either. So this is, we need to look into that. So the challenges, as also Jörg and Peter mentioned, was to upscale this DED laser beam wire from the lab to industrial production. And initially, what we wanted was to jump from 1 kilo per hour deposition rate to 10 kilos per hour. That was the initial goal. And we wanted to maintain equal mechanical and corrosion properties. So we were very ambitious on this. And yeah, in the end, we ended up around 5 kilos per hour, as Peter mentioned. So I think as in all learning processes, we have like different paths. So, you know, we have smooth and rose paths, but also we had some difficulties, as also Peter mentioned. But it was very interesting anyway, as learning is amazing in this, with these materials and this process. So we had a bit of everything, as in life. So the first challenge were these fine grain areas. So when we were depositing in the very beginning, we found that these very small grain areas close to the bottom of the deposited bit. So they were placed in the bottom. We said, what is that? That was driving, you know, squeezing our minds. What is that? In some cases, these fine grain areas were together with voids or pores, lack of fusion. So it was not only the presence of these fine grain areas, it was also that sometimes they were associated to other type of imperfections or defects. Then we realized that there was a relationship between the presence of these fine grain areas and the parameters that we were using. So this is just a cross section, but we were using different parameters. As you can see, with these parameters, just with this cross section and optical microscope, we could easily see that there was more concentration of these areas than when we were reducing the wire feed speed and the productivity, let's say, the amount of kilos per hour that we were. So we found that there was a correlation. Something is happening in, you know, the process and the microstructure. We need to find out what's happening. Peter already explained, but that is in parallel what we were developing together. So we also prepared experiments where we were changing the deposition rate, so from higher to lower, until we found, okay, which could be a good deposition rate, or, you know, so that we are free from this fine grain area. So as you know, as I told you, we were looking into different conditions in the same build, changing conditions and trying to identify the good or optimum operational window. Then when we looked closer into these fine-grained areas, we found that they were mainly austenitic areas with high concentration of intermetallics all around. These intermetallics are highly enriched in chromium and moly. So then as a consequence, you know, all the areas around that are depleted on these elements, and that is why they become less good for corrosion properties. But the reason was, as also Peter explained, this partially molten wire. So we were feeding the wire, but not all the wire was fully molten. So then that it was identified that this feeding system was pushed to the limits, and for some, I don't know if the milliseconds is accurate, but for some short times, there was no resistance heating in the wire, and then it was not really melting properly. So that was the first challenge we found, was very interesting. And then we found another challenge, which were the hot cracks. As I show you in the very beginning, this is the typical microstructure that we can expect when we have a very fast cooling rate. You know, very, fully ferritic microstructures, all these dark is ferrite, and then very, very thin grain boundary austenite forming here in the edges. And also we saw, of course, in the areas where we were reheating and were suffering from this heat, we found some secondary austenite, and also, interestingly, a lot of epitaxial growth. So some grains were coming from, you know, were even having the same, we could identify the same grain progressing towards 1, 2, 3, 4 layers. So it was really long grains, as I will show you now, here on the right. So these grains were super, 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 super long. And the amount of austenite in the boundaries was very little. So that with the austenite, as I told you also in the very beginning, has very little, has more, is more ductile. And then if we have very little austenite in the grain boundaries, then we can end up with these hot cracks, because there is no possibility for the microstructure to absorb all these stresses. Then the final demonstrator looked like this, and the microstructure after solution annealing. So we went into, of course, solution annealing before analyzing all these properties that I will show you now. Looked like this, well balanced or reasonable balance, good microstructure. Then when we look into the corrosion properties, you know, our target values were according to Alfa Laval's standard. So as you can see, the different samples in the different orientations according to this pitting potential testing succeeded with the requirements. So it was okay. From the tensile testing, also we test in the different directions, and all these samples also succeeded with the requirements. So that was also good things. And impact toughness, we had 6 samples tested also in the different directions, and also succeeded with the minimum requirements by Alfa Laval. Then the conclusions is that from our side is that the process, this DED laser beam wire, allows high deposition rates, but there are challenges such as this partially molten wire, the voids or pores that happen at high wire feed speeds. Hot cracks are normally not a problem in conventional welding for duplex, but it's a problem, or we have seen this as a problem in hot cracks. This very thin austenite and also the possibility that nitrogen is lost during the deposition are facilitating this phenomenon. And the last conclusion is that we proved that with this test that this deposited material met the corrosion, tensile, and impact toughness requirements, but not the fatigue requirements. So I haven't shown you any result that was not, the material was not meeting this fatigue requirements. So the lessons learned in this project might lead to future work to go ahead and hopefully in the future meet these fatigue requirements too. And if you want to know more, there is already a paper published in Welding in the World by Springer, so you can read more if you are interested to dig more into the microstructural aspects. Thank you.
Great, thank you, Asun. Okay, so now we're moving on to a final presentation of this webinar, and I would like to hand over to Klaus Felixson from University West, who will tell us about the sustainability aspects in traditional machining versus additive methods. So please.
Thank you. So here we go. I'd like you to think a little bit about the origin of this project that I've been part of. It's a project that's run for several years with a lot of industrial partners, and of course we have focused a lot on the practical issues and to get these things built and develop additive manufacturing for this application together with Alfa Laval. The name of the project, though, is SustainablE Steel Additive Manufacturing, SESAM. So it's only fair that we also consider the sustainability properties that we have. So I've been working in parallel, we can say, with the experimental work and try to estimate and have an idea of the sustainability properties. Let me just say that I work normally at University West, and my approach is to look at environmental sustainability in terms of energy resources that go into the processes and the carbon equivalent footprints that results from this. And I have a fair number of student projects and publications in this area, so I've listed a few of them there. This project that we're talking about today, though, is one out of several sustainability projects that concerns additive manufacturing. As we promised in the original Vinnova application here, we hope to contribute to a sustainable industry by doing this. And also the result was supposed to be a contribution to sustainability here in developing from TRL5 towards production situation. So with that in the background, I can also say that I have a background working in Cambridge with a company that does materials intelligence and materials data. So I've used their software in trying to estimate energy use and carbon footprints of the materials that we talk about. And here's an overview of the kind of thing that I study. So we can see here I've circled the material, the duplex stainless steel that we have been working with in this project. And you can see here that the embodied energy, the energy it takes to produce 1 kilo of this steel quality from the mining, including all the transports and metallurgic processes and so on, is listed on the x-axis. And as expected, this leads to carbon emissions, and translated into carbon equivalent emissions. We can see on the y-axis that for all these materials that I've listed here, not only stainless steel, but there's a correlation. So the more energy you use to produce the material, the more carbon footprint we will also have. But you can see here that the stainless steel that we're talking about is on the lower half of the diagram here. So I would say it's a low or medium eco-property material. And many of the materials that we work with here at PTC is aerospace materials. So high strength aluminiums, and there's titanium, for example, and nickel-based super alloys. They are considerably higher in environmental footprint because they take much more energy to produce. But staying with the stainless steel here, we have a number of options. We can study the virgin material, or we can study the recycled material. All of this is included in the database. Or we can work with the typical sort of industrial average mix because if you buy duplex stainless steel, there will be a fraction of recycled material already from the supplier. So I have been working with what I call typical grade here, which contains then the sort of an average fraction of recycled materials, and it results in lower carbon footprint and lower energy use, of course, than the virgin material. So what have I done then? Well, since I've been working with students in parallel with this project, I have been interested in studying the typical example and comparing traditional machining methods with additive manufacturing that we have been doing in this project. So we can see here an overview for 2205 duplex stainless steel, where we start with the first sort of original piece of material. And then with the students, I've explored what happens if we want to machine away most of this and just keep a cylinder of materials instead. And there's a lot of energy that goes into machining this, of course. And it's also interesting to study the case where we have a bowl, so a more circular sort of cylindrical, circular symmetric structure, as you can see in figure 3 here. So these are not exactly the structures that we've been doing in this project, but they are similar, and the sort of the shapes that we have been building in this project is related or similar to the cylindrical cases that I have studied here as an example. What have I done then? Well, I've tried to mimic the sizes of the final additive manufactured product that Alfa Laval has. And we can see here some of the data that I've been using. The students that I've had has also made CAD images of that. So you can see that the final result will be some kind of cylindric, thin wall stainless steel, or a bowl that results from this. And the calculations then, well, first I've estimated the embodied energy because I focused on the energy, since that is the origin of the carbon footprint, and I will consider the carbon footprint a bit later. But the energy is the main thing, and the energy of item 1 there, the original part, can be estimated from the data in the database and the assumptions that I've made. And it ends up that the embodied energy, the energy it takes to produce the amount of material that we have as the original here in figure 1, is about 52 gigajoules in total. Now, the machining will contribute to the energy, so I've added to this 52 gigajoules an estimate of the coarse machining energy that is needed to remove most of the material. And as Alfa Laval has pointed out, that this is a great source of waste, because you remove most of the material in this process. I can see that this sort of increases the total energy to an estimated there 66 gigajoules for the machined final component. And that's the cylindrical case. I've also did a similar calculation for the bowl structure, and I arrive at a very similar value, because it's similar amounts of materials involved in this. What about the carbon footprint then? Well, in the database, there is also estimate of the industrial average carbon equivalent emissions resulting from the different materials. So using the data for the typical grade of material here, it turns out that it's about 5 kilos of carbon dioxide equivalent emissions per kilo of produced stainless steel. And this means that for our case here, if we consider all the emissions from the original part there, the number 1 in this figure, it will come to around 1 ton of carbon dioxide. And of course, if you are in Sweden and use Swedish processes and so on, it is nearly carbon neutral. So there are not much carbon emissions coming out from from use of electric sources in Nordic or Scandinavian situations. Okay, so this is the traditional situation, traditional machining. I have then used some approximate data and projections from PROCADA that have been building this this structure, and we can see here that materials. We can see here that for the building time that we have in one of the final experiments, it's about 45 hours. We can see that the one main contributor is the laser power that we have from the disc laser we have at the University West here, and the hot wire process that is inherent in the PROCADA equipment. So it comes to about 6.5 gigajoules of laser and electric use, with associated very little carbon emissions from that. A main source of energy and carbon emissions is the argon that is used to protect the process during the build. And we have not made any efforts in this project to try to limit or recycle the argon. So it has been quite a generous flow of 250 liters per minute or so, which amounts to more than 40 gigajoules in the total build time, because it's such a long process. I have also talked to the producers of the welding wire that is used in the additive manufacturing, and that's for Alpine. They produced a wire of diameter 1.2 millimeters in our project, and the total material weight in the final product, with a little bit of margin for fine machining, is estimated to be around 155 kilograms. And this can be reduced as we develop the process to give more and more accurate sort of builds. But using this weight, 155 kilos, we arrive at non-renewable energy used to produce the wire in this case is about 11 gigajoules. And then we get a total, if we add all these sources, the laser, the argon, necessary argon energy and carbon footprints, and together with the energy to produce the welding wire in the AM method, we arrive at a sort of a total energy of around 60 gigajoules. So this is a little bit lower or very similar to the estimates for the traditional machining. And let's see, I have used the sources then of the database that comes from ANSYS selector that I've been working with in Cambridge. I've also used direct data from the environmental data from the suppliers of the welding wire, and PROCADA direct experimental data. So the conclusions is that we can see that the additive manufactured component from PROCADA has similar, or maybe even in some cases lower total energy than the comparable traditional machine ones that we have studied in the student project. I know that Alfa Laval is using a forging method, so there will be some important differences there. But in this case, we find that the protective argon gas has the largest contribution to the energy use, and therefore also the carbon footprint. There's a great potential to save this by recycling or being more careful with the argon use, obviously. So we can reduce a lot the energy use by doing that. And we can increase the accuracy as time goes on here. This was used with the demonstrator that we have produced and some early and approximate estimates that we have. And we can conclude also that if the processes are taking place in a Nordic and Swedish energy environment, there will be very low greenhouse gas emissions from those parts. So the energy use, of course, is connected to the costs and the effort to produce this, but it's not necessarily serious for environmental greenhouse gas considerations.